Hello, today we're going to be looking at Inscribed theorem. So to help us understand this theorem, we need to have some background on a couple of things. One, the secant line. So secant line basically goes through and touches a circle 2 times, while a tangent line touches the circle only once. And so we have what we call an inscribed angle. An inscribed angle can be made up of 2 secant lines, or it can be made up of a secant line and a tangent that intersects on the circumference of a circle. We also have what we call a central angle, and which is an angle whose vertex is at the center of the circle, whose sides pass through the point on the circle's circumference, therefore subtending an arc. And when we do this, we can have the inscribed and central angles being the same subtended arc. So for example, we may have something that looks like this, and we may also have it look like this. And so maybe this is A, B, C, and O. And in this case, they both share an arc AB, right? So angle C and angle O both share this same subtended arc AB. Arc being just kind of a section of the perimeter, or the section of the circumference of a circle. Much apologize if you're hearing some noise. They're doing some construction here at the school. So with this, we can also have something that looks like this, where these are not necessarily shared subtended arcs. They're not necessarily shared arcs. So if this was A, B, C, and this is D, E, F, angle E does not equal necessarily angle B, and they're not sharing the same subtended arc, right? Angles B subtended arc is AC, while angles E's is arc DF. So taking this a little further, let's start looking at a couple more things that we need for the angle inscribed theorem. So the theorem itself states, so let me just type this out for us. Theorem. The theorem states the measure of, and let's make that a little wider, measure of an angle inscribed in a circle is half the measure of the arc it intercepts. So you want to note that this is equivalent to the measure of the inscribed angle is half the measure of the central angle if they intercept the same arc. Right, so basically what that is saying is that if we have that circle from above, if I have this circle and we have these different measurements, and the intersecting on the, so this inscribed angle intersects on the circumference, and then we have this central angle, and let's say this is A, B, C, and O. And here we're saying O is the center of the circle. Well, we could say in something like this, basically what the theorem is stating is, maybe we'll call for, is we could say, well, maybe we'll call angle O alpha. And what it's saying is this angle C is half of alpha. So this would be alpha divided by 2. And we could see this maybe written down in a couple of different ways. You might see something like 2 of angle C is equal to angle O, or you might see something like angle C is 1/2 of angle O. So there's a couple ways you might see this. And so what we want to do now is we want to prove this statement. So that's what it states, but we want to prove it and not just go off of what somebody else has told us. But we want to prove it and understand it at the depth of why this works out. So I'm going to, let's actually just copy what we did up here. And let's paste it down here. Okay, that didn't work. Okay, so it doesn't look like it's going to want to copy and paste easily. So let's just, we can duplicate it quick enough. So we'll draw a circle. And we will draw in our inscribed angle. And we'll draw in our central angle. Right? Remember, our central angle is located at the origin. And we'll call this A, B, C, and we'll call this O. And for this exercise, we'll say C, so we'll let C be an inscribed angle, and we'll let angle O be a central angle, and we will say let both angle C and angle O subtend arc AB. So from here, what we are going to do is we're going to just kind of exploit our shape sum. We are going to first draw in a line from C to O. Let's see about changing the color of that some so it stands out to us. So we've drawn in this line. It goes from C to O now. And what we draw line CO, and by so doing we've actually have now created two isosceles triangles. And how we know this is since O is at the center of the circle, line AO, line BO, and line CO are all radii. So therefore, right, these are all the same distance because they're all the radius of the circle that we are looking at. So for this case, let angle ACO equal x, and let angle BCO equal y. So we'll call this x and we'll call that y. Now something we know about isosceles triangles are that our bases are the same. So therefore angle A is equal to x, and I'll just want to move this a bit. So angle A is also equal to x, and angle B is also equal to y because of definitions of isosceles triangles. So we'll call that y and we'll call that x. With that being said, what we can now look at is that this angle, let's say BOD or BOC, sorry, let BOC, actually no, correction, let's call that D right there. So let BOD be equal to 2y. And the reason why we can say that it is equal to 2y is through the exterior angle theorem. And using the same reasoning, we'll let angle AOD equal 2x. Once again, this is through the exterior angle theorem. And I can do another video on the exterior angle theorem if you would like. Well, that means angle BOA is equal to 2y plus 2x. And if we factor that out, we could look at it as 2 times x plus y. So we got this angle BOA equals 2 times x plus y, but we also know angle BOC was just equal to x plus y. And so we now have seen that this central angle is twice as big as the inscribed angle. And that is the end of our proof.